Hello and welcome back to Let's Code Physics. Last time we began the process of trying to find the inner and outermost points of a planet's orbit around the star. The technical name for these points are the aphelion and perihelion. I'm sure you'll let me know if I'm mispronouncing those. The idea that we're looking at is that a planet going around a star experiences an effective potential shaped like the red curve here, where the attractive part is due to the gravitational force between the planet and the star, and the repulsive part is due to the conservation of angular momentum pushing the planet back away from the star. The last time we were working, we developed and ran a code to successfully find the aphelion, the farthest point from the star. That's this intersection right here. The green line here indicates the energy level, the total energy of the star. So the star is of the planet going around the star. So the planet's forbidden from going over this way or from going over this way, because that would require it to have a negative a negative kinetic energy. And the way we set this up was with a simple function and bracketing method. So the function we're setting up is the effective potential here. Here's the repulsive conservation of angular momentum term. Here is the attractive gravitational term. Here's our constant energy level. In order to do this, we have to give an estimate of the left bound and right bound for the intersection. So from the graph, we read off 1.5 and 2. We know that this aphelion is somewhere in between the two. And then it's a simple bracketing code where we take the difference between the two. Not the difference between the two. Well, we take the difference between the two to see whether we've approached an acceptable tolerance value. We take the midpoint between the two bracketing values, evaluate the potential at that point, and find out whether we find out whether the intersection is in the left half or the right half, and based on that we adjust the right bound or the left bound accordingly. And then at the end of the code, our code is going to print the values for us. So we've done that, so this is capable of finding one of these two. Now we want to set it up to where we can find both of them at the same with the same run of the code. So what we're going to do is we're just going to copy this. Actually, let's copy the whole thing. We're just going to copy. Let's copy that print statement as well. We are going to copy the entire thing. Let's see. There we go. All right, so let's label that as find aphelion. And here we're going to go down here and we're just going to call this find perihelion. Paste. All right, so this is all the new stuff. We're going to find the perihelion. So we need to do something here to figure out our left and our right. So that part's going to have to change because obviously I need different bounds on this side than I had on this side. And so basically we just have to change all the reference from aphelion to perihelion, because the code itself works out the same way. It's just the input values we're going to have to change. So we're going to change this to a peri. There we go. And so now what I have to do is I have to think about how I'm going to tell it what the bounds are. So I need to give it a range for the aphelion, and I need to give it a range for the perihelion, which means at minimum I'm going to need 3 different points. I'm going to need to give it a leftmost bracket, a rightmost bracket, and somewhere in between the aphelion and perihelion. So let's start thinking about that up here. Set leftmost bound, rightmost bound, and a midpoint, or maybe I should say a point between aphelion and perihelion. There we go. So why don't we call those, let's give those some different names. We're already using R left and R right here. Why don't we call those R min, R max, and we need something in the middle. I'm already using an R mid down below, so I'd hate to have to go down and change all of those. So why don't we, let's see, let's just call that maybe R middle. There we go. Yeah, that works out. R middle, I kind of like that. Or R muddle, because if you get confused, it's probably muddling. So for example, for this problem, we could identify 0.5 pretty easily as a minimum value. We could identify 2 as a maximum value, kind of like what we had before. And our, oh, whoops, I just set the wrong thing. Oops, our R max 2.0. So actually, how about we take these and put them in the order from left to right. Hey, score 1 for usability. Let's see, for the middle, I can read off 1 pretty easily from here, so let's put in a 1.0 there. So for this section where we find the aphelion, actually let's do a little bit of rearrangement here. Here we go. So now this is part of the find aphelion part. Oh, fair aphelion. Let's see. So for the aphelion, for the farthest point, the left side is going to be our middle. Not riddle, our middle. And the rightmost part is going to be our max. Okay, and I don't need to change anything else about the code. Just going to keep scrolling down. For the find perihelion, now we know what to do. The R left is going to be our min. The R right is going to be our middle. Boy, I really want to type riddle. So I must be in the mood for a riddle. Please leave a riddle in the comments. So our left is going to be the very minimum value. Our right is going to be the middle value. Okay, cool. And so then everything else should remain the same. I scroll down. So it's going to print for me aphelion and perihelion. Now, judging from the new plot graph, I can see that the perihelion is going to be about 0.69 something, and this is going to be about 1.78 something. All right, so 0.69 and 1.7. Please remember that because I probably won't. All right, let's run this code and see what we get. Oh, and I forgot to, it printed out the value that I wanted, but I forgot to tell it to put a new line at the end of here. And then just for safety's sake, we'll put a new line at the end of there. There we go. That'll make it easier to read. We run. Okay, cool. So our perihelion was 1.80, so that's about 1.79 something. And our aphelion, excuse me, is 1.80. Our perihelion is 0.69. And most importantly, we get the correct energy value, so those are intersecting the energy curve at negative 0.4. And so this is a pretty good match. If I wanted to make this match a little bit better, all I have to do is decrease the tolerance. So right now it's got a relative tolerance of 10 to the minus 3. So let's try a 10 to the minus 4. Save and run. Now we can't tell it, but it's going to take a little bit longer. It might take, an extra step. And lo and behold, we do get, one significant digit closer to negative 0.4. That also makes these folks change, out here in the 1, 2, 3, 4, 5th decimal place. So this basically determines, how many decimal places accurate your answer is. So we are on our way to a nearly complete solver. The only issue we've got now is that I'm having to specify these 3 points. What it would be really nice to do would be if I could set this to be something ridiculously low, this to be something ridiculously high, and not have to specify something in the middle. What if I can't get a very accurate graph, or what if I can't read it off of a graph? What we're going to do next time is we're going to add in another part to the code that finds this minimum. Once we can find the minimum, then that can be our middle value, because obviously this is going to be between the perihelion and the aphelion. So thank you very much for watching. I'll see you next time. Bye-bye.